Yes.
So, just a question, sir, general question regarding tests.
Hmm.
So, is this in this semester, is this best out of anything? Because because of continuous evaluation.
No, it probably won't be best. You will have to give three tests, and all the three scores will be considered.
So, will there be any compensatory tests?
One already happened, right? For those who missed out for whatever medical or emergency reasons, because of that, whoever missed out the first test, for them compensation test was already made, like it was already conducted.
Okay, sir. Okay. Thank you,
Yeah,
sir.
yeah. So let us continue with our discussion. So what we have done so far is just to see omega fp. We started from there, a random experiment omega fp. Then we defined random variable. Okay. So with the random variable, we had these discrete and continuous. That's the classification. Then you have PMF, and here you have PDF, and then you learn cumulative distribution functions. You learn moments, correct? Expectations, and you learned moment generating functions of these random variables, and you learn spatial distributions here, right? And then what did we do? We moved further and we went into this. So here you learn transformations also, right? Through transformations, we learned a lot of random variables. Then we did random vector, and like in random variable, we will do random vector. So we had seen discrete random vector in the last class. Today, what we want to do is we want to start with continuous random vector. And in the discrete random vector, we had seen the concept of joint PMF, correct? After joint PMF, you had done something which is called as marginal PMFs. Once you did marginal PMFs, then we had done something like independence of random variables, correct? Once we did independence of random variables, then we saw that expectation of xy is equal to expectation x expectation y. So independent implies this, but the converse is not true. Then we had seen several such things, that x1 up to xn iid, and then we had done x bar, what is the distribution of x bar, and so on and so forth. What else did we do? We also did something which is called as weak law of large numbers, right? So that weak law of large numbers kind of gave you the justification or the quantification of the fact that there are certain intuitions in your mind, like averages works better or averages are safer, and why those averages are safer. So that was given to you by weak law of large numbers. So we want to do similar things again for continuous random variables. So in continuous random variables also, again we'll do this joint PDF, marginal PDFs. So one thing that we did not do for discrete random variables that I want to do is we will do joint CDF also. Okay. So the similar concept that I do here will be applicable in case of discrete random vectors also. So maybe I'll start with this joint CDF concept for the continuous random variables. Then we'll do joint PMS, marginals, independence. Then we'll do some interesting properties like we did for discrete random variables. So like we saw in discrete case, n independent Bernoulli random variables are added, you get a binomial density. So like that distribution of x plus y, distribution of x divided by y. These are the type of things that we will look at in this particular case of continuous random variables. And that will give rise to various ways in analyzing certain very important distributions that will come later on in this course. Okay. And like transformations here, we will want to do transformations here, right? So this is something that we want to do. So this is the agenda now. So similar to discrete random variable, this is something that we want to cover now. Okay. So this is what we want to do. So in the coming 2-3 classes, this is what we'll mostly focus on. So just to like quickly recap and remind you of what we have done. So let us start looking at this continuous random vectors. Okay, joint continuous random vector. So let x and y be continuous random variables on the same probability space. Okay. So this capital F of xy, which is the joint CDF basically, is defined as probability x less than or equal to x and y less than or equal to y. Okay. So this is what it is for minus infinity less than x and y less than infinity, meaning that x and y are real numbers taking any value. So this particular function is called as joint CDF, okay, joint cumulative distribution function of x and y. And one of the important things, I think this is something that you have seen in your advanced calculus course also, but this is a rectangle R that I define in the Cartesian space xy, a less equal x less equal b, and c less equal y less equal b. Okay, so just to be little bit sure, I will just take open interval at one side. Okay, in this case it is not going to matter much, but really. So this is my A to B, and suppose this is my C to D, then this is the rectangle that I am really looking at. And in this rectangle, so this is the rectangle that I am looking at, and one thing to remember is that A is strictly less than X. Okay, so this line and this line, the red lines, these two red lines are excluded from this rectangle. Okay, so this is how I define this rectangle. And why I define this rectangle, obviously you understand by now why I am looking at this rectangle. So probability of xy belonging to R, probability of xy belonging to R is basically then probability of A less than x less than or equal to B, and C less than y, the random variable y less than or equal to D, right? So probability of a random vector xy now. So I have already written this random vector xy here that belonging to R. So this is basically, you can quickly check, it is f of BD minus f of AD minus f of BC plus f of AC. Okay. So using this joint CDF, it is very easy. Like, so this area basically. So if you have a point XY, like this point X naught Y naught. So in general, in a in a in a plane, suppose this is the point XY you have, X naught Y naught, say for example. Then what is capital F of X naught? All the points such that A is less than or equal to X naught and Y is less than or equal to Y naught, right? So basically you are looking at this open rectangle, correct? And this shaded region is what basically you are looking at. Is that right? This is what basically you are looking at. So you are looking at this particular dotted shaded region, and you are looking at probability of this dotted shaded region. That is what you are looking at when you evaluate. So the probability of this part is basically f of a, right? So probability of this part, blue shaded region, is basically joint CDF evaluated at the point x naught y. I hope you understand this. And once this is understood, then you can just see at these 4 points I am really looking. So at these 4 points of the rectangle, I am really looking at what is happening, right? So these 4 points of the rectangle I see, and now you see this is the point BD. So rectangle like this, then AD, then this part to the left is removed, and so on and so forth, right? So you subtract the area below CD, you subtract the area below this point AB, right? So that is what you have to look at, right? So this formula I think is useful. So basically you are adding these areas, right? So this is the area you are looking at, and then this is the area, these 4 points to the left of these 4 points you are looking, right? So once you are looking at this and this area gets subtracted twice, so you will add this area once. So that is basically what you are doing. So once you understand this, I guess this formula is clear to all of you. So this,
Sir, it should be
yes,
f of AC, right?
where
In the last term, f of a
the
comma c.
f of a comma c gets subtracted twice, so you have to add f of ac once again. That's right. So what did? Oh, sorry, I wrote it. If ab does not make sense, f of ac. You are right. Yeah, thank you. That is what you should have. Thank you, Yash. So this is the formula, right? This is how you will evaluate probabilities with this joint, and then similar to marginal PDF, you can talk of marginal CDFs. Okay, and what this marginal CDFs will be, capital F of x is probability x less than or equal to x is same as fx, and y component is actually infinity, which should be same as limit y tending to infinity f of xy. Okay, so this particular is basically the marginal CDF of random variable x, and similarly you can define marginal of y also. So this will be probability capital Y less than or equal to y is basically f infinity and y, which is same as limit x tending to infinity f of xy, right? So from the figure it becomes really easy, right? So another important thing, now then I will define joint density. I'll define the joint CDF in the following way, right? So if there exists a non-negative function f of xy over R2 such that capital F of xy is equal to integral minus infinity to x integral minus infinity to y f of uv du dv. Okay, try to draw parallels of this with one variable calculus or one variable random variable, like one dimensional random variable. There exactly same thing we had done, but we had only one variable x. So we had only one integration. Here you have double integration because you have function of two variables x and y, right? So this is what we have. Then f of xy is called as joint PDF, is called as joint PDF of this random vector x and y, right? Joint PDF of this random vector x and y. And once you define this, there exists a non-negative function is important. So you have said already that it's a non-negative function. So it is like anti-derivative concept extended to the function of two variables, right? And basically f of u is what you find out in this way. So similarly, what you will say, so probability of this random vector ay belonging to some region A, what is this probability? This probability is basically equal to a f of xy dx dy, right? So that is how you will calculate. And clearly you can check clearly integral minus infinity to infinity minus infinity to infinity f of xy dx dy will actually be equal to 1. Okay, and del square by del x del y. So second order derivative of this capital F of xy will be equal to f of xy. Okay, so this is something that you can check. So you substitute x and y as infinity in both these places, then you know that first you will get the marginal CDF of x maybe, and then you will get this goes to infinity, right? As x goes to infinity, that value will go to 1. That is the property of CDF in one dimension that we had already stated, right? So we'll use that property. So using these properties, you can show this part, and similarly using simple differential calculus, you can show this second part also. Okay, so these are the things that I think which are very much in parallel with one dimensional random variables. So I have just extended it to the two-dimensional random variable. So like R is equal to 2 here in this particular case. Okay. And in case of continuous random variables, we'll mostly stick to R is equal to 2, though R if you have a general R, then I hope you understand what you will do is basically you will have R integral, right? Rather than double integral, like double triple, you will have R integral. So that is what you will have, right? So that's something that you have to understand. So let us take an example. So what is this example saying? So let this random vector xy. So you please notice sometimes I'm writing it as a column, sometimes I'm writing it as a row. So just to make sure that you get comfortable with both the type of notations that you will see. Okay. So this xy denotes the random vector. The random vector representing the coordinates of randomly chosen point. In the circle with center at 0, 0 origin and radius r. Okay. So what is happening? You have this center at origin and radius r circle. So this is the circle that you are talking of. This is r. And what is this random vector xy denoting? So you choose any point xy. So this is the point xy. The random vector xy is going to denote the coordinates of this point that are chosen. Okay, so the point that is randomly chosen, if you see the example that we had seen earlier, was basically measuring the distance of this point to the bullseye, right, to the origin. So that gave us random variable. Because the distance was only one real number, right? So it can take value anything between 0 to r. That's what we said. And now what we are saying? We are saying that you look at the point, and rather than looking at the distance from the origin, you record what are the coordinates of that particular point, right? So the coordinates are x and y. So let this random vector be such that it will have its coordinates. Okay. So now what I'm going to do, corresponding to this random variable, I'm going to define the density. Okay. So if f of xy, the density is equal to c, constant, for xy, the point xy belonging to the circle. Otherwise, it is equal to 0. So suppose this density is given, then obviously the question is find C. What is this C? Okay. So what is this C? So we know that integral minus infinity to infinity f of xy dx dy has to be equal to 1. So this means that integral, now you have x and y, right? So this x and y, so I will just write out on this entire circle, c dx dy has to be equal to 1. So what is the value of c?
1 by the area of circle.
1 by the area of circle, because this circle, if you integrate dx dy, you know, using the double integration that you learned in advanced calculus course, you know that you will get the area of the circle, right? So that's the property of double integration that I'm using. So this will mean that c is equal to 1 upon pi r square, because I already know that r is the radius, right? So what does this joint density becomes? It becomes 1 upon pi r square for xy belonging to the circle and is equal to 0 otherwise. Very interesting density. How will this density behave? So let us see once again. Okay, so what do we have? We have this, and we have a circle of radius r, right? So this is the circle of radius r. This is the radius r. Xy is going to denote the coordinates of the point randomly chosen in this circle. And what is the density? The density is given by f of xy is equal to 1 upon pi r square. Okay. So can you tell me how is the graph of this density going to look like? How is the graph of this density going to look like?
The uniform density.
Correct.
So it
It
will
will
be a
be
plane
a
over the circle.
Exactly. What it will be? It will be a plane over the circle. Plane meaning a flat plane, right? So not a oblique plane or something. It will be a flat plane parallel to the xy axis itself, parallel to the xy plane. And what height this plane will be? The height of the plane will be at 1 upon pi r square, right? So the graph of the density, if you see, will be like this. And now in case of this particular thing, when you are asking of probability, when you are asking of probability of certain subset here, so suppose this is the subset whose probability you are asking, what will be the probability of this subset? The probability of this subset is basically what you are supposed to do. You are supposed to look at the roof, you see how the roof is, and you are going to compute the volume bounded by that roof above this red region, right? Above this red region, whatever is the volume bounded by that roof, that's what you are basically going to look at. Do you understand how I'm getting at the generalization? In case of one random variable, what you are looking at? In case of one random variable, you are looking at a subset like this. Then you are looking at the roof. The roof was basically a curve. And what were you looking at? You are looking at area bounded by this curve and these lines, right? That's what you are looking at. So you are looking at area below the curve. Here in this particular case, what you are looking at, you are going to look at volume below the surface. And when you generalize this to 3 dimensions, 4 dimensions, 5 dimensions, you know what is really going to happen. So do you understand what is happening here? How you are going to look at this joint probability density function? So the joint probability density function in case of two random variables will be a surface. It will be a surface above xy plane, right? So that surface can be a surface which extends over a finite region like this, or it can be a surface which extends to the infinite region xy plane entirely, right? It can go like that. It doesn't matter. So in this particular example, 1 upon pi r square is what you are getting. So that is above the circle. So in the xy plane, this is the circle. So again, what is the range of this random vector? The range of this random vector obviously is this circle, right? So this is the point where the density is non-zero. Beyond this circle, the density is equal to 0 by definition, right? So the range of this random vector is basically this circle. You choose a subset of this. So what is the probability that the randomly chosen point xy lies in this red region? So how will you calculate that? So suppose you denote this area by a, the region by a, then do you all agree that this is equal to a fxy dx dy, which is nothing but geometrically volume below the surface. What is the surface? Volume below the surface, z is equal to f of xy, and above the subset A, right? Above the subset A. So this is what basically you are looking at. In this particular case, what it will be equal to? It will be equal to basically this probability will be dependent on this area of A, right? So this probability will be dependent on this area of A. So if you choose two subsets of equal area here, because the roof is flat, the volume bound by these two areas will be same, which is equal to the probability. So this is uniform probability, right? So this is uniform joint PDF. Okay, this is uniform joint PDF. This is what it is. Okay, so this is how you will evaluate the probabilities also. So once you understand this, then what is the next question I'm going to ask? So just to write down, so the probability of xy belonging to this A is basically area of this A divided by pi r square, right? And that is coming out because of this uniform probability principle, right? So this is basically A fxy dx dy. So this is the calculation that we have. So what is fxx now? Which is basically fx infinity, which is same as limit y tending to infinity capital F of xy, right? So this is something that you can have. So you can calculate what is capital F of xy, and you can calculate this. What I'm going to do is I'm going to find out the marginal density first. Okay. So the marginal density is minus infinity to infinity. I integrate dy, right? So in order to find out this, I integrate dy. This definition is similar to what we have already seen, right? So this is marginal PDF of x, correct? In general, yeah, this is the marginal PDF of x. Okay. So what will this be equal to? So what is the range of y? So in here, you can check this is the y-axis. So the y varies from this point to this point, right? What is this point? This point is 0 minus root of r square minus y square. Sorry, r square minus x square. And this is 0 plus root of r square minus x square, right? So the range of y basically in the integration, I'm going to okay, let me draw this diagram again, then it will be clear. So what I'm really going to do, is this. I have this, and then what am I going to do? I am going to look at this particular thing, right? So I am going to integrate for a fixed x, fx, for a fixed x, I am going to integrate with respect to y. And where is y going to move from? Y is going to move from root of minus r square minus x square to plus root of r square minus x square, right? That is the range of y, right? On this line, the lower point of y to upper point of y. That is what is going to happen. So this is going to happen for a fixed x. So this is the x that is fixed, and that is what I'm going to do. So this is the range of y. So I hope you understand what I'm doing. To root of r square minus x square. And what is the fx? So 1 upon pi r square dy, right? And integration is easy. 1 upon pi r square comes out, and then you have constant, which is symmetric function. So 2 times root of r square minus x square divided by pi r square. And what is the range of x? The range of x is minus r less than x less than r. Because if you see from where to where x is going, so this x can go from here to here, right? So this is the limit point, right hand side, left hand side. So this is minus r and this is r. That is what I'm doing. So is this part clear? What I'm really doing? So if you want to draw parallels of this with the random vector thing that we had done, you can see that in the case of random vector, you had a discrete table, so to speak. X and y discrete table was given. Here, x and y, the table is, so to speak, continuous, right? X is taking continuous values from minus r to r, and y is also going to take continuous values from minus r to r with the constraint that they lie in the circle, right? With the constraint that they lie in the circle. So you have this continuous table. So the continuous table, what is the typical xy coordinate? So typical xy coordinate in this continuous table is this, right? So this is one point, which is a typical point. And when I want to find out marginal of x is for a fixed x, I integrate the y out. So you take summation of all the y's for a fixed x. That's what you did in case of PMF. So that summation will change to integration. And you can see that for this particular fixed x, you will integrate about on this, you will integrate. So taking summation is basically you will do integration in continuous case, right? So along this green line, you will integrate. So the range is from minus root r square minus x square to plus root of r square minus x square, and x will vary from minus r to r. So these are the possibilities, and the same logic I can apply to the f also. So I'll write down marginal of f. So what will be the marginal of f? Marginal of f is basically you will integrate the x variable out, right? So you'll integrate the x variable out. So this is basically marginal PDF of y. So this is what you have. And again, if you want the figure, then you will fix some y, and for that y, so this is the y you fix, and for that y you will integrate. So the integration will be from this point to this point, right? So you will, the limits of x will be from this to this. So the limits of x will be root of r square minus y square to root of r square minus y square. 1 upon pi r square dx, right? So this is what you will get, and because of symmetry, you'll get 2 times root of r square minus y square divided by pi r square. This is your marginal of y. And what is the range of y? The range of y is going to be from minus r to r. Y can take values on this vertical axis, right? So minus r less than y less than r. That is the marginal PDF of y. That is what you have. So this is equal to 0, otherwise that is how you have to define. So you have to define it for entire real life. So this is equal to 0, otherwise. Okay. So I hope this concept of obtaining marginal PDFs from the joint PDFs is clear. And once you know this marginal PDFs, then the immediate thing that we had done for the case of discrete random variables, we can do for continuous random variables, we can define independence. So how do we define independence? So the way we define independence is x and y are called as independent random variables, are called as independent random variables. If and only f of xy, the joint density is actually the product of marginals, correct? So the joint density, so I will say joint PDF is product of marginal PDFs, correct? So in this example, in this previous example, what are the joint PDFs? The joint PDFs are fx and fy. They do not give the product 1, right? So clearly in the previous example, x and y are not independent, correct? X and y not independent. Okay, but there is a easy way to generate examples, right? What is the easy way to generate examples? You start with two densities x and y, you just take their product, you get the joint density. And what is the assumption that you make? The assumption that you make that is x and y are independent, right? Then you can get many more densities like this, right? So this is something that is really very useful, right? So easy way to generate examples. So this easy way I am writing because this is in tune with the doubt somebody had asked me in the last class, right? In that table, PMF table, you were so easily confused that the probability x is equal to small x, y is equal to small y has to be px into py, right? That's how you were thinking, but there you had inherently assuming the independence, right? Inherently you are assuming the independence of random variables x and y, and every time it is not the case. As I had shown, I had started with a joint PMF where x and y random variables are not independent, right? So that confusion was there, so that is why I am once again writing this thing. So let x and y be two independent continuous random variables. Okay, with PDFs fxx and fy. Okay, respectively. Then what do? I define the joint PMF of xy as fxx into fyy, correct? So I will do this. So clearly the conditions for this PDF are it should be a non-negative function for every xy. That is true. Why is that true? That is true because you are taking product of two non-negative functions. And what will be this double integral fxy xy dx dy, right? Minus infinity to infinity. That is what you want. But because you have defined this f of xy in this way, fxx fyy dx dy, this will be actually minus infinity to infinity fxx dx integral minus infinity to infinity fyy dy, which will be equal to 1 times 1, which is equal to 1, right? So this has to be equal to. So both the conditions for joint PDF are satisfied, that this should be equal to 0 and this double integral of this joint density f of xy dx dy has to be equal to 1. So these two conditions which define a joint PDF, they both are satisfied by this, and hence this f of xy is actually solved. Won't it happen? Okay. So f of xy is actually the joint PDF. Okay, so this is an easy way to generate the joint densities. So immediately one example of this easy way of generating joint densities. Let us take n to be normal 0, 1 and y also to be normal 0, 1. Okay, so x and y are these. Let x and y be independent. Okay, let x and y be independent. Okay, then what are we going to do? Okay, so you know that the density of x is basically 1 upon root 2 pi e to the power minus x square by 2 minus infinity less than x less than infinity. And similarly, phi y is 1 upon root 2 pi e to the power minus y square by 2 minus infinity less than y less than infinity. Then I define f of xy to be equal to product of these two densities, phi x times phi y, which is equal to 1 upon 2 pi e to the power minus x square plus y square divided by 2 for minus infinity and infinity bounds for x and y. Correct? So this is a new joint density. This is the new joint density that we have. And how does this density graph really look like? So how does this density graph really look like? So how do I explain? So on the xy plane, that you have, this is the xy plane, suppose, and on the xy plane what you really have is a okay. So is does this does this give you the idea, like? So it is kind of inverted. It's kind of a bell, right? The center of the bell is at the point 0, 0, and it's a bell, but the interesting part of this bell is that it is extending towards all infinities, all the sides of infinities, right? X, y, in any direction you go in the xy plane away from 0, the roof of the bell actually dies down. It is going to 0. The interesting fact is that this surface will never touch xy plane ever. Correct? This surface will never touch xy plane ever, because for no value of x and y, this function is actually equal to 0. So it is always going to be above the xy plane, and the peak comes at the point 0, 0, and it goes down, right? It goes down like this. So this is how the surface of the density really looks like in this particular case. Very interesting density. This particular density fxy is actually called as joint normal, and we'll explore more about this joint normal. But this is one easy way of generating a joint normal, right? But this is not the only way. So let us take another example.
Excuse
Okay,
me,
so
sir.
yes.
So I wanted to ask one thing. There's one doubt. Sir, can I say that if two probabilities are independent, their functions are the single-valued functions? Like if the probability of x is
No,
just a
the
value,
first
just
thing,
a function
no,
of
no.
x.
Yes, the first thing that you have to understand is that we are not saying probabilities are independent. Okay, we have not defined independence of probabilities. We have defined independence of two things: independence of events and independence of random variables. And independence of random variables was motivated from the definition of independence of events. Now, with this, what is the question you want to ask?
Yes, sir. I'm sorry for making a term wrong. Sir, what I wanted to ask is, sir, here probability of x. I'm saying x and y are independent.
Uh,
Probability such that x equals to x is, and probability such that y is equal to y, both of them are the random variables are independent. So what I wanted to ask is phi of x, can we say that is just a function of x?
phi of x is only function of x anyway.
No, I'm saying that given that x and y random variables are independent, can I conclude that the
Phi
probability
of
of,
x is a marginal function of x. Do you agree? Phi of
yes,
x is a marginal function of x. Do you agree?
yes, sir.
So when you compute the marginal density, here also, even if you did not have independence, marginal of x is only a function of x. You see here, marginal of x is only a function of x. It will not be a function of y ever, because you are integrating out y. No?
Okay. Oh, the y term will never stay. Okay.
Y term will never be there in the marginal of x, because you are integrating out y. So same thing as you are summing out all possibilities of y given that x was small x, right? So that entire row you are summing out, or entire column you are summing out, right? So that's exactly same thing that you are doing. You are integrating out entire column or integrating out entire row. That's what you are doing. So marginals will never be functions of the other random variable. It's not only about independent. For any marginal, that is always true. Is that okay, Yash?
Yes, sir. Thank you, sir.
Okay. So let us look at another example. Okay. So let x and y.
Sir, I had a question about the joint normal.
Yeah.
So is the joint normal the same as the normal for one variable which is revolved around an x-axis or y-axis?
Yeah, you can think of it that way also. Yeah.
Like if you revolve the graph or the function.
But yeah, but only in this particular case, only in this particular case. So I'm going to take example of a joint normal again. So this is the next example I'm writing, and it's not as easy. Here it is very nicely done, beautifully done. N is 0, 1, y is also 0, 1, x is also 0, 1. It is not necessary that x and y should be 0, 1 only. I can have x is equal to 0, 1, y can be 5, 3. Normal 5, 3. You take the product, then you whatever you get, it will also be a joint normal, and its graph will not be the way you want to construct now. But here it is possible because of symmetry in x and y. Everything is nicely done about x and y. Is that okay, Shashank?
Yes, sir.
Yeah. So in this particular point, your observation is correct. In this particular case, if you really want to visualize that way, it is fine. But every time a normal density, joint normal density may not look like what you're saying. So let x and y be joint density. Suppose this as joint density f of xy is equal to c into e to the power minus x square minus xy plus y square divided by 2 for this range of x and y. Okay. So the question is find this particular constant c. Okay. So how do we find this c? So the first thing that we do is we know that double integration is equal to 1. So what you can do the double integration and equate it to 1, and by doing this double integration you will see what you are really going to get. Okay, so that's fine. That's one way of doing it. But I will do it in a slightly different way. I will look at the marginal of x. Okay, marginal of x, and I'll go through that approach. Okay, so marginal of x I'll look at. So what is the marginal of x? Marginal of x is integrate y over its range. So the range of y is this. Integrate f of xy dy. Correct? So this is marginal of x. So c comes out minus infinity to infinity e power minus x square minus xy plus y square divided by 2 dy. Right? That is what I have. And if you carefully look at this exponent, I am going to do something which is called as completing the square tricks of the exponent, right? So what I am going to do, I am going to look at these two terms, y square minus xy, right? And this term is not a complete square, but it is almost a complete square, right? So I need to add something to this so that it becomes a complete square. And what will I add to this so that it becomes a complete square? Is it not x square by 4? We have done this completing the square tricks before, right? So that is x square by 4. So if you allow me, I'll write this thing down as exponential of y minus x by 2 whole square plus 3x square by 4, right? I have split the remaining x square in this particular divided by 2 dy, right? So that 1 by 2 is still there outside the bracket. And now what I am going to do is c e to the power minus 3x square by 8. This comes out, and what remains inside is minus infinity to infinity e power minus y x by 2 whole square dy, right? And this divided by 2. So what is this integral? Can anybody tell what is this integral? Root 2 pi, correct. Why is this integral root 2 pi?
So y minus x by 2 equal to z, and then it becomes distribution. So
Correct. So
1
this
by
is
root
a
2 pi.
normal density. So if you really want to look at it, what you are looking at, so this red highlighted box basically is the almost, okay, PDF of normal x by 2 1, right? Almost. So if you really want, I can write it down. What is the factor that is missing? The factor that is missing is root 2 pi, right? So this is root 2 pi times PDF of this. So the integral will be equal to root 2 pi, correct? So you have fx x is basically equal to c into root 2 pi into e power minus 3x square by 8. Is that right? Minus 3x square by 8. So this is true for minus infinity less than x less than infinity. That is what you get for fx. So from here, can you tell me what is c? Can you tell what is c from here?
So by integrating it to 1, we can.
So I want to avoid integration. Suppose I want to avoid integration, then what will I do? Obviously, I will integrate from minus infinity to infinity. I should get 1. So if I do that, then I will know what is the value of c. But I want to avoid integration, then what will I do? So this is something you have to get used to now. This is something.
Root 3 by 4 pi.
X plus root 3 by. Yeah, same. The substitute.
Root 3 by 4. Correct. Why is that?
The substitute x by.
So it's again a normal distribution, so you just integrate it. The only difference
Correct.
is
So
like
what is
that 3 by 8 terms.
so this is PDF of which normal density? So looking at this exponential factor, it comes out as a PDF of which normal density? You tell. You are right. Those who
Sigma
give
square is
answer.
4 by 3.
What is mu? Mu is equal to 0. Sigma square is equal to 4 by 3. Correct? That is what you have. So if you have this, then what is the PDF? So this is my guess. So what is the PDF of normal 0 and 4 by 3? Can anybody tell what is the PDF of this? 1 upon sigma root 2 pi. So what will I write down? 1 upon sigma, so 3 by 4 root 2 pi. Correct? That is what I'll write down. Is that fine? Is that fine? 1 upon sigma
Yes,
root
sir.
2 pi e to the power minus x minus
So
mu divided by
we have taken sigma square to be 4 by 3.
yeah. So
So
I'll
it will
have
be
a
actually
square
root
root.
of that.
I'll have a square root here. 1 upon sigma root 2 pi e to the power minus 1 by 2 into x minus mu, which is 0, divided by sigma square, right? So divided by sigma square is 4 by 3. So this will be equal to root 3 into 2 root 2 pi e to the power minus x square 3x square by 4. And you have almost all the terms here, right? So you have almost all the terms here. So you compare this star with double star. And from there, what is the value of c that you get? What is the value of c that you get from here? Do you get this value as c? So if you get c like this, then I suppose you will get what you have here, right? So this part basically has to be equal to this part. That's what you have. That is how you have to choose c. So you choose c in this particular way, and your job is done, right? So this is how you can do this. So now one thing that you have to understand from this calculation, is that you have to be really very careful. Okay, so I have been telling you to prepare a chart, put it beside your bed, read it every time. So now you see these are the type of calculations we'll do very frequently in this course. So I'll quickly look at this, and from observation I'll declare c is equal to this. I'll just look at the MGF and I'll tell what is the random variable I'm talking of. So if you are not remembering all this formula that we have done so far, then it becomes difficult. Okay, so now the trick of being able to see these things is to work out these examples again and again, to look at these forms of PDFs, PMFs, MGFs, CDFs, expectations, parameters, all those things you should know really very well now, so that you can quickly do these type of calculations. I am purposefully not doing integration at this step. I could have done integration minus infinity to infinity fx dx equal to 1 and could have computed what is the value of c. I am sure almost all of you will be able to evaluate that integral using gamma function formula, and then you will be able to show what is the value of c, that you will get it equal to root 3 by 4. But I want you to compare this. I want you to see this slowly. You should be able to identify these things, because this is what is really going to be important. Okay, so this is something that is the key. So please make sure that you are doing these things and you are writing down your formulae and all these things every day, reading them at least once, and so on and so forth. Okay, so this is important. So now we'll move to the next topic, which we had done in the case of discrete random variables. We'll do it for the case of continuous random variables also. So what we really want to do is we want to look at distributions of sums and quotients. Okay, so this is what we want to do. So we want to look at distributions of sums and quotients of the random variables. So let x and y be continuous random variables with the joint PDA f of xy. Okay, so this is the joint PDF f of xy of this continuous random. So define this random variable z, new random variable z, as phi of xy. Okay, so this is the new random variable z. In particular, we are interested in two types. Psi of xy is equal to x plus y, and this phi of xy is equal to x divided by y. Okay, so in particular we are interested in these two transformations, but in general you can have any transformation phi of xy which gives a new random variable z. Then what we really would do for a fixed z, for a fixed z in R, what would you do? We are interested in the event. What is the event we are interested in? We are interested in the event this capital Z is less than or equal to small z. Why are we interested in this event? We are interested in this event because capital Z less than or equal to small z. So okay, so here one thing that you have to understand is psi is a function from R2 to R. Okay, so psi phi is a function from R2 to R. Okay, so you are going to real number. So Z is a random variable that you will obtain from the random vector xy, right? So for example, Z can be equal to x plus y. So x plus y will take real values only. It is not a vector. X plus y is a scalar random variable. Similarly, x divided by x square plus y square. These are the type of examples of phi xy that I am talking about. And in order to find out the density of this capital Z, what we are interested in this particular event, because this particular event will give rise to what? It will give rise to the cumulative distribution function CDF of Z. And once you have CDF of Z, then you can find out PDF of Z by differentiating. This is same logic that we had used in the transformations earlier, right? So now this is the event that I have. So I define by AZ being a subset of R2. Because this Z is related to X and Y, I'll relate this event to the event which is subset of XY plane, right? So that is my AZ. Okay, so this define AZ to be set of all XY such that phi of XY is less than or equal to Z. So basically I am looking at this particular thing that is given, and once I understand what is this set F, this set AZ, then let capital FZ be the cumulative distribution function of Z if you denote it by capital Z. Then FZZ is basically equal to probability z less than or equal to z, which is same as basically probability of a xy, the random variable xy belonging to this set az, which is nothing but integral over az f of xy dx dy. Is this calculation clear to all of you? This is extremely important. Once you understand this calculation, then you will be able to like find out PDF of any function phi of xy. Okay, any function phi of xy. So please make sure you understand this calculation. This is all I am going to do today, and then we'll use particular cases of phi xy and see how this integration actually looks like, and that's what we'll do. But make sure that you understand this concept today. So is this concept clear to all of you? Please read this. Please think about it. Is this okay? Do you all agree? Can you all visualize what we have done here?
Yes, sir.
Okay, in that case, we'll stop here. You again go back and you again look at this last 2 pages, because tomorrow we'll pick up from here. Okay, so this is the point where we'll start in tomorrow's class. So make sure that you understand these things. Okay, and before you